In Euclidean geometry, a Platonic solid is a regular, convex polyhedron with congruent faces of regular polygons and the same number of faces meeting at each vertex. 5 solids meet those criteria, and each is named after its number of faces. Geometers have studied the mathematical beauty and symmetry of the Platonic solids for thousands of years. They are named for the ancient Greek philosopher Plato, who theorized in his dialogue, the Timaeus, that the classical elements were made of these regular solids. History. The Platonic solids have been known since antiquity. Carved stone balls created by the late Neolithic people of Scotland lie near ornamented models resembling them, but the Platonic solids do not appear to have been preferred over less symmetrical objects, and some of the Platonic solids are even absent. Dice go back to the dawn of civilization with shapes that augured formal charting of Platonic solids. The ancient Greeks studied the Platonic solids extensively. Some sources credit Pythagoras with their discovery. Other evidence suggests that he may have only been familiar with the tetrahedron, cube, and dodecahedron, and that the discovery of the octahedron and icosahedron belonged to Theaetetus, a contemporary of Plato. In any case, Theaetetus gave a mathematical description of all 5 and may have been responsible for the first known proof that no other convex regular polyhedra exist. The Platonic solids are prominent in the philosophy of Plato, their namesake. Plato wrote about them in the dialogue Timaeus c. 360 BC, in which he associated each of the 4 classical elements with a regular solid. Earth was associated with the cube, air with the octahedron, water with the icosahedron, and fire with the tetrahedron. There was intuitive justification for these associations. The heat of fire feels sharp and stabbing. Air is made of the octahedron. Its minuscule components are so smooth that one can barely feel it. Water, the icosahedron, flows out of one's hand when picked up, as if it is made of tiny little balls. By contrast, a highly non-spherical solid, the hexahedron, represents Earth. These clumsy little solids cause dirt to crumble and break when picked up, in stark difference to the smooth flow of water. Moreover, the cubes being the only regular solid that tessellates Euclidean space was believed to cause the solidity of the Earth. The 5th Platonic solid, the dodecahedron, Plato obscurely remarks. The god used for arranging the constellations on the whole heaven. Aristotle added a 5th element, Aethema, and postulated that the heavens were made of this element, but he had no interest in matching it with Plato's 5th solid. Euclid completely mathematically described the Platonic solids in the Elements, the last book of which is devoted to their properties. Propositions 13-17 in Book 13 describe the construction of the tetrahedron, octahedron, cube, icosahedron, and dodecahedron in that order. For each solid, Euclid finds the ratio of the diameter of the circumscribed sphere to the edge length. In Proposition 18 he argues that there are no further convex regular polyhedra. Andreas Spiza has advocated the view that the construction of the 5 regular solids is the chief goal of the deductive system canonized in the Elements. Much of the information in Book 13 is probably derived from the work of Theaetetus. In the 16th century, the German astronomer Johannes Kepler attempted to relate the 5 extraterrestrial planets known at the time to the 5 Platonic solids. In Mysterium Cosmographicum, published in 1596, Kepler proposed a model of the solar system in which the 5 solids were set inside one another and separated by a series of inscribed and circumscribed spheres. Kepler proposed that the distance relationships between the 6 planets known at that time could be understood in terms of the 5 Platonic solids enclosed within a sphere that represented the orbit of Saturn. The 6 spheres each corresponded to one of the planets. The solids were ordered with the innermost being the octahedron, followed by the icosahedron, dodecahedron, tetrahedron, and finally the cube, thereby dictating the structure of the solar system and the distance relationships between the planets by the Platonic solids. In the end, Kepler's original idea had to be abandoned, but out of his research came his 3 laws of orbital dynamics, the first of which was that the orbits of planets are ellipses rather than circles, changing the course of physics and astronomy. He also discovered the Kepler solids. In the 20th century, attempts to link Platonic solids to the physical world were expanded to the electron shell model in chemistry by Robert Moon in a theory known as the Moon model. Combinatorial properties. A convex polyhedron is a Platonic solid if and only if all its faces are congruent convex regular polygons, none of its faces intersect except at their edges, and the same number of faces meet at each of its vertices. Each Platonic solid can therefore be denoted by a symbol p, q, where p equals the number of edges of each face and q equals the number of faces meeting at each vertex. The symbol p, q, called the Solar currency fleece symbol, gives a combinatorial description of the polyhedron. The Solar currency fleece symbols of the 5 Platonic solids are given in the table below. All other combinatorial information about these solids, such as total number of vertices, edges, and faces, can be determined from P and Q. Since any edge joins 2 vertices and has 2 adjacent faces, we must have. The other relationship between these values is given by Euler's formula. This non-trivial fact can be proved in a great variety of ways. Together these 3 relationships completely determine V, E, and F. Note that swapping P and Q interchanges F and V while leaving E unchanged. Classification. The classical result is that only 5 convex regular polyhedra exist. 2 common arguments below demonstrate no more than 5 Platonic solids can exist, but positively demonstrating the existence of any given solid is a separate question, one that an explicit construction cannot easily answer. Geometric proof. The following geometric argument is very similar to the one given by Euclid in the Elements. Each vertex of the solid must coincide with one vertex each of at least 3 faces. At each vertex of the solid, the total, among the adjacent faces, of the angles between their respective adjacent sides must be less than 360 degrees. The angles at all vertices of all faces of a Platonic solid are identical. Each vertex of each face must contribute less than 360 degrees per 3 equals a 120 degree. Regular polygons of 6 or more sides have only angles of 120 degree or more, so the common face must be the triangle, square, or pentagon. And for triangular faces, each vertex of a regular triangle is 60 degree, so a shape may have 3, 4, or 5 triangles meeting at a vertex. These are the tetrahedron, octahedron, and icosahedron respectively. Square faces. Each vertex of a square is 90 degree, so there is only one arrangement possible with 3 faces at a vertex, the cube. Pentagonal faces. Each vertex is 180 degree. Again, only one arrangement, of 3 faces at a vertex is possible, the dodecahedron. Topological proof. A purely topological proof can be made using only combinatorial information about the solids. The key is Euler's observation that, and the fact that, where P stands for the number of edges of each face and Q for the number of edges meeting at each vertex. Combining these equations one obtains the equation. Simple algebraic manipulation then gives. Since is strictly positive we must have. Using the fact that P and Q must both be at least 3, one can easily see that there are only 5 possibilities for geometric properties, angles. There are a number of angles associated with each Platonic solid. The dihedral angle is the interior angle between any 2 face planes. The dihedral angle, I, of the solid P, Q is given by the formula. This is sometimes more conveniently expressed in terms of the tangent by. The quantity h is 4, 6, 6, 10, and 10 for the tetrahedron, cube, octahedron, dodecahedron, and icosahedron respectively. The angular deficiency at the vertex of a polyhedron is the difference between the sum of the face angles at that vertex and 2I. The defect, I, at any vertex of the Platonic solids P, Q is. By a theorem of Descartes, this is equal to 4I divided by the number of vertices. The 3-dimensional analog of a plane angle is a solid angle. The solid angle, I copyright, at the vertex of a Platonic solid is given in terms of the dihedral angle by. This follows from the spherical excess formula for a spherical polygon and the fact that the vertex figure of the polyhedron P, Q is a regular q-gon. The solid angle of a face subtended from the center of a Platonic solid is equal to the solid angle of a full sphere divided by the number of faces. Note that this is equal to the angular deficiency of its dual. The various angles associated with the Platonic solids are tabulated below. The numerical values of the solid angles are given in steradians. The constant I equals /2 is the golden ratio. Radii, area, and volume. Another virtue of regularity is that the Platonic solids all possess three concentric spheres, the circumscribed sphere that passes through all the vertices, the midsphere that is tangent to each edge at the midpoint of the edge, and the inscribed sphere that is tangent to each face at the center of the face. The radii of these spheres are called the circumradius, the midradius, and the inradius. These are the distances from the center of the polyhedron to the vertices, edge midpoints, and face centers respectively. The circumradius A and the inradius R of the solid P, Q with edge length A are given by, where I is the dihedral angle. The midradius I is given by, where H is the quantity used above in the definition of the dihedral angle. Note that the ratio of the circumradius to the inradius is symmetric in P and Q. The surface area, A, of a Platonic solid P, Q is easily computed as area of a regular polygon times the number of faces F. This is, the volume is computed as F times the volume of the pyramid whose base is a regular polygon and whose height is the inradius R. That is, the following table lists the various radii of the Platonic solids together with their surface area and volume. The overall size is fixed by taking the edge length, A, to be equal to 2. The constants I and I3/4 in the above are given by. Among the Platonic solids either the dodecahedron or the icosahedron may be seen as the best approximation to the sphere. The icosahedron has the largest number of faces and the largest dihedral angle, it hugs its inscribed sphere the most tightly, and its surface area to volume ratio is closest to that of a sphere of the same size. The dodecahedron, on the other hand, has the smallest angular defect, the largest vertex solid angle, and it fills out our circumscribed sphere the most. Symmetry, dual polyhedra. Every polyhedron has a dual polyhedron with faces and vertices interchanged. The dual of every Platonic solid is another Platonic solid, so that we can arrange the 5 solids into dual pairs. The tetrahedron is self-dual. The cube and the octahedron form a dual pair. The dodecahedron and the icosahedron form a dual pair. If a polyhedron has the currency Flees symbol P, Q, then its dual has the symbol Q, P. Indeed, every combinatorial property of one Platonic solid can be interpreted as another combinatorial property of the dual. One can construct the dual polyhedron by taking the vertices of the dual to be the centers of the faces of the original figure. Connecting the centers of adjacent faces in the original forms the edges of the dual and thereby interchanges the number of faces and vertices while maintaining the number of edges. More generally, one can dualize a Platonic solid with respect to a sphere of radius d concentric with a solid. The radii of a solid and those of its dual are related by. Dualizing with respect to the midsphere is often convenient because the midsphere has the same relationship to both polyhedra. Taking D2 equals R yields a dual solid with the same circumradius and inradius. Symmetry groups. In mathematics, the concept of symmetry is studied with the notion of a mathematical group. Every polyhedron has an associated symmetry group, which is the set of all transformations which leave the polyhedron invariant. The order of the symmetry group is the number of symmetries of the polyhedron. One often distinguishes between the full symmetry group, which includes reflections, and the proper symmetry group, which includes only rotations. The symmetry groups of the Platonic solids are known as polyhedral groups. The high degree of symmetry of the Platonic solids can be interpreted in a number of ways. Most importantly, the vertices of each solid are all equivalent under the action of the symmetry group, as are the edges and faces. One says the action of the symmetry group is transitive on the vertices, edges, and faces. In fact, this is another way of defining regularity of a polyhedron. A polyhedron is regular if and only if it is vertex uniform, edge uniform, and face uniform. There are only 3 symmetry groups associated with the Platonic solids rather than 5, since the symmetry group of any polyhedron coincides with that of its dual. This is easily seen by examining the construction of the dual polyhedron. Any symmetry of the original must be a symmetry of the dual and vice versa. The three polyhedral groups are the tetrahedral group T, the octahedral group O, and the icosahedral group I. The orders of the proper groups are 12, 24, and 60 respectively, precisely twice the number of edges in the respective polyhedra. The orders of the full symmetry groups are twice as much again. See for a derivation of these facts. All Platonic solids except the tetrahedron are centrally symmetric, meaning they are preserved under reflection through the origin. The following table lists the various symmetry properties of the Platonic solids. The symmetry groups listed are the full groups with the rotation subgroups given in parentheses. Hithoff's kaleidoscope construction is a method for constructing polyhedra directly from their symmetry groups. They are listed for reference. Hithoff's symbol for each of the Platonic solids. In nature and technology, the tetrahedron, cube, and octahedron all occur naturally in crystal structures. These by no means exhaust the numbers of possible forms of crystals. However, neither the regular icosahedron nor the regular dodecahedron are amongst them. One of the forms, called the pyritohedron, has 12 pentagonal faces, arranged in the same pattern as the faces of the regular dodecahedron. The faces of the pyritohedron are, however, not regular, so the pyritohedron is also not regular. In the early 20th century, Ernst Haeckel described a number of species of radiolaria, some of whose skeletons are shaped like various regular polyhedra. Examples include Cercoporus octahedrus, Cercogonia icosahedra, Lithocubus geometricus and Cercohegma dodecahedra. The shapes of these creatures should be obvious from their names. Many viruses, such as the herpes virus, have the shape of a regular icosahedron. Viral structures are built of repeated identical protein subunits, and the icosahedron is the easiest shape to assemble using these subunits. A regular polyhedron is used because it can be built from a single basic unit protein used over and over again. This saves space in the viral genome. In meteorology and climatology, global numerical models of atmospheric flow are of increasing interest, which employ geodesic grids that are based on an icosahedron instead of the more commonly used longitude-latitude grid. This has the advantage of evenly distributed spatial resolution without singularities at the expense of somewhat greater numerical difficulty. Geometry of space frames is often based on Platonic solids. In MERO system, Platonic solids are used for naming convention of various space frame configurations. For example, a 1/2 O plus T refers to a configuration made of 1/2 of octahedron and a tetrahedron. Several Platonic hydrocarbons have been synthesized, including cubene and dodecahedrane. Platonic solids are often used to make dice, because dice of these shapes can be made fair. 6-sided dice are very common, but the other numbers are commonly used in role-playing games. Such dice are commonly referred to as DN, where N is the number of faces. See dice notation for more details. These shapes frequently show up in other games or puzzles. Puzzles similar to a Rubik's Cube come in all 5 shapes. See magic polyhedra. Liquid crystals with symmetries of Platonic solids. For the intermediate material phase called liquid crystals, the existence of such symmetries was first proposed in 1981 by H. Clannett and K. Markey, and their structure was analyzed in. See the review article here. In aluminum, the icosahedral structure was discovered 3 years after this by Dan Shechtman, which earned him the Nobel Prize in Chemistry in 2011. Related polyhedra and polytopes. Uniform polyhedra. There exist 4 regular polyhedra which are not convex, called Kepler or poinsett polyhedra. These all have icosahedral symmetry and may be obtained as stellations of the dodecahedron and the icosahedron. The next most regular convex polyhedra after the Platonic solids are the cuboctahedron, which is a rectification of the cube, and the octahedron, and the icosahedron, which is a rectification of the dodecahedron and the icosahedron. These are both quasi-regular, meaning that they are vertex and edge uniform and have regular faces, but the faces are not all congruent. They form two of the 13 Archimedean solids, which are the convex uniform polyhedra with polyhedral symmetry. The uniform polyhedra form a much broader class of polyhedra. These figures are vertex uniform and have one or more types of regular or star polygons for faces. These include all the polyhedra mentioned above together with an infinite set of prisms, an infinite set of antiprisms, and 53 other non-convex forms. The Johnson solids are convex polyhedra which have regular faces but are not uniform. Regular tessellations. The three regular tessellations of the plane are closely related to the Platonic solids. Indeed, one can view the Platonic solids as the 5 regular tessellations of the sphere. This is done by projecting each solid onto a concentric sphere. The faces project onto regular spherical polygons which exactly cover the sphere. One can show that every regular tessellation of the sphere is characterized by a pair of integers p, q with 1/p plus 1/q greater than 1/2. Likewise, a regular tessellation of the plane is characterized by the condition 1/p plus 1/q equals 1/2. There are 3 possibilities: 4 which is a square tiling, 6 which is a triangular tiling, and 3 which is a hexagonal tiling. In a similar manner one can consider regular tessellations of the hyperbolic plane. These are characterized by the condition 1/p plus 1/q less than 1/2. There is an infinite family of such tessellations. Higher dimensions, in more than 3 dimensions, polyhedra generalize to polytopes, with higher dimensional convex regular polytopes being the equivalents of the 3-dimensional Platonic solids. In the mid-19th century the Swiss mathematician Ludwig Currency discovered the 4-dimensional analogues of the Platonic solids, called convex regular 4 polytopes. There are exactly 6 of these figures. 5 are analogous to the Platonic solids, while the 6th one, the 24-cell, has one lower dimension analogue, the hexagon. In all dimensions higher than 4, there are only 3 convex regular polytopes, the simplex, the hypercube, and the cross polytope. In 3 dimensions, these coincide with the tetrahedron, the cube, and the octahedron. See also. Notes. References: Attiaor, Michael. And Sutcliffe, Paul. Polyhedra in Physics, Chemistry and Geometry. Milan J. Math 71, 33 Euro 58 doi, 10.1007 per second 00032-003-0014-1. Carl, Boyer. Mosbch, Utah. A History of Mathematics. Wiley. ISBN A0-471-54397-7. Coxeter, HSM Regular Polytopes. New York, Dover Publications. ISBN A0-486-61480-8. Euclid. Heath, Thomas L., ed. The 13 Books of Euclid's Elements, Books 10 Euro 13. New York, Dover Publications. ISBN A0-486-60090-4. Haeckel, E. Kunstform and der Natur. Available as Haeckel, E. Art Forms in Nature, Bristol, USA. ISBN 3-7913-1990-6. Hecht, Lawrence. Stevens, Charles B. New Explorations with the Moon Model. 21st Century Science and Technology. PA 58. Kepler Strinus Adonive Sexangular, 1611 paper by Kepler which discussed the reason for the 6-angled shape of the snow crystals and the forms and symmetries in nature. Talks about Platonic solids. Anthony Pugh. Polyhedra, A Visual Approach. California, University of California Press Berkeley. ISBN A0-520-03056-7. Well, Herman. Symmetry. Princeton, New Jersey, Princeton University Press. ISBN A0-691-02374-3. External links, Platonic solids at Encyclopedia of Mathematics, Weierstein, Eric W., Platonic solid, MathWorld. Book 13 of Euclid's Elements. Interactive 3D polyhedra in Java. Solid Body Viewer is an interactive 3D polyhedron viewer which allows you to save the model in SVG, STL or OBJ format. Interactive Folding Unfolding Platonic Solids in Java. Paper models of the Platonic solids created using nets generated by Stellar software. Platonic solids free paper models, Nets, Grime, James Steckles, Katie. Platonic solids. Numberphil. Brady Heron. Teaching Math Without Student-Created Models, Teaching Math Without Teacher Instructions for Making Models, Frames of Platonic Solids. Images of algebraic surfaces, Platonic solids with some formula derivations,